Okay, in the last chapter, chapter 4, we looked at delay routines. Whereas in this chapter, chapter 5a, we look at interrupts. What is an interrupt and how do we prepare for interrupt? How do you set up interrupt and how do you service an interrupt routine? We look at that one. So pick interrupts. What is an interrupt? So an interrupt is an event that forces the microcontroller to temporarily stop the main execution of the main program. So it will execute the current instruction and stops the main program execution and calls a interrupt service routine. So what does that exactly mean? Let's look at this diagram. This is our main program. Main program starts here and your microcontroller is executing the main program. While it's executing this instruction, an interrupt occurred. Okay. What type of interrupt, how it occurs, we look at in a minute. An interrupt occurs. So what the microcontroller does is finishes the current instruction and it then saves the next address on the stack. You just put them in the stack. And then it automatically jumps to this particular address. That is where interrupt vector is stored. That way it picks up the address where the interrupt service routine is. So it knows by going here where the address is and jumps to that part, and that's where you have the interrupt service routine. And it services the interrupt. So it's executing a main program, an interrupt came, it leaves the main program, finishes the current execution, goes to the service routine and does the service routine. After that it will return to the main program. I'll come back to that in a minute. So that's what it says here. On interrupt, the return address of the main program is automatically pushed onto the stack and then it then picks up the service routine address, interrupt service routine address, and then it executes that. So it's important when it finishes its interrupt service routine, it sees the last instruction as RETIFRE, interrupt service routine ends. So it knows the interrupt service is finished. So what it needs to do is that it needs to leave from here and come to the stack and pick up the return address. It knows where to pick up and it picks up from the stack and goes to that particular address. By putting that value into the program counter, it picks up that address and then it continues its main program. So you can see a computer is executing a main program. At that point an interrupt comes, it stores the next one into the stack and jumps out of that and go and service your interrupt service routine, and when it finishes the interrupt service, come back, picks up this address and go here and continue to the main program. So that's how the microcontroller does that. So how does it know it has finished the interrupt service routine? You must have that particular instruction at the end of the service routine. So we will do an example in a minute. So in the PIC microcontroller, there are many types of interrupts, and we will look at like two interrupts for the moment. One is the external interrupt at port B, the 0 bit, that pin 21 of it, where you can give a pulse that will cause an interrupt. That will disturb the main program. It will go to the interrupt service routine. That's one interrupt. We will be learning that. The second interrupt is timer. There is a counter timer inside, and when the timer has timed out, it will cause an interrupt. And we will learn that as well, how to do it. So there are two types of interrupt. There are other type of interrupts as well available, which we will look at them when you do your project. At the moment, we just do these two interrupts. Once you have the understanding of these two interrupts, you should have no problem doing the other type of interrupt. Each of the above interrupt causes an interrupt flag bits. So there's a flag corresponding to each interrupt, and that bit is either 1 or 0. And it will, when an interrupt happens, that flags are set most of the time. And we, by looking at that, flag bit, you will know an interrupt has happened. So interrupt flags must be searched in your program to find out which interrupt flag caused the interrupt, because the interrupt could be any one of these. So in your program, you need to look for this which one caused the interrupt. And then, once the interrupt service has serviced, then you must make sure you have finished the interrupt, then you should clear the flag bits, otherwise it will cause the interrupt again. So you clear the flag bit before you return to the main program. And it's very important that a certain pattern need to be followed. And this is called the Enhanced Universal Synchronous Asynchronous Receiver Transmitter. That's for communication purposes. And when you do the project, you'll be using this one. Let's move on to the next slide. So interrupt system registers. What are the registers available? So the main one, what we call is interrupt control register, is called INT-CON. And the second one is called the peripheral interrupt request. And this particular register records all the interrupt requests. And this register has individual and global interrupt enable bits. So in order to receive an interrupt, you're going to enable. Once the interrupt has occurred, then it will set a flag. So there are a couple of steps that you need to follow. So if you take, for example, the following interrupt flags are contained in this particular register. There are other registers as well. So interrupt pin interrupt. So int pin interrupt. What does that mean? You can look at that particular interrupt. How does that happen? So you can see in the port B, there's an external interrupt enable bit there. So if you want to receive an interrupt on port B, you must make sure that this particular bit needs to be set to 1. So in your software, you should access this particular register and bit 4 should be set to 1 in order to receive an interrupt externally. And if you want to enable all the interrupts or particular interrupt, you need to go to this particular register and you enable them, means you need to make sure that's set to 1. And if you have a timer, we talked about timer 0 flags. So if you want to enable the timer interrupt, you need to go to TOIE bit, that is that bit, and that bit need to be set to 1 for the timer interrupt to be registered. So if you don't enable those interrupts, they won't happen. So it's important in your initialization, you must make sure you have enabled the interrupts. So this register should be used for most of the enabling. There are other registers as well, but this one is, for the moment, is enough for you to use. So this is located in bank 0 and the address is OBH. And if the overflow has occurred in the timer, then it will set 1 into this bit. So if you check that bit after you have enabled the timer bit, and if you check that bit, if that bit is 1, then you know an interrupt has occurred. That means a timer has been, it's timed out really. So I won't go through all these in detail. At the moment you can actually read and when you're writing the program, but it's important that you must enable the interrupt at the flag bits. Then you check certain bits to see whether the interrupt has occurred. Okay. So the second one I suggested, the second is interrupt request registers. And if you take the int-con register, earlier I said that to you, TOIE is to enable the timer interrupt, and this one to check whether interrupt has occurred. If you are dealing with timer 1 and timer 2, mostly you'll do timer 0 first. So there are 3 timers inside there. Timer 0, timer 1, timer 2. We will learn this first, and then this one, do it with the project, you can do that. Timer 0 is only, you need to know only that particular address to manipulate. And timer 1, you need to know this particular address. That's called PIR1, which is the peripheral interrupt flags. And you can see the flags are here, timer 1 and timer 2 flags are. Similarly, there are other ones as well. So these registers, you need to look at them. And for example, if you are dealing with the interrupt flags for these interrupts, then you must look at PIR1, the first register. This is this one. If you are look at for these interrupts, flag bits, and they are in PIR2, that's in this location. So these are on the data sheet, but just to let you know that two things you do for interrupt setting up. First one is you enable the interrupt. Second one, you check for certain flag bits and see whether the interrupt has occurred or not. Now, when you are setting up an interrupt, so let's take this particular microcontroller, and it has got here RB node. That's your port B register, port B position, RB node, and say that we have got a 5 volts here, and there's a switch here. If you look at this switch, it's always 1. When you press the switch, it goes down. So it's like a falling edge. You could have it connected the other way around. It will be a rising edge as well. So you can actually program this particular register to tell that by setting this to 1, if you set this to 1, then the microcontroller knows that it will be only interrupt will occur for the rising edge. If you set this one to 0, this is set to 0, then the microcontroller knows that interrupt can occur only on the falling edge. So you can program which edge you want to detect by setting this particular bit. So that's called, the option register has got interrupt edge select bit. And you can select that bit, and by selecting it, you can make the microcontroller interrupt to occur for a positive edge or negative edge, which is very, very important if you are doing a counting. So there are a number of pulses coming in, and you want to count how many pulses have arrived. Or you want to count how many pulses within 2 seconds you're getting. And then you decide, every time I want to count on a positive edge or negative edge. And depends on this bit. If you can select this one as a positive edge, that's as a negative edge, and every time there's an edge comes, a counter will count. So counting number of pulses can be done very cleverly, and when it has counted the full register value, then it'll give a flag. Then it causes an interrupt. So what I'm going to do is that the easiest ways to explain this principle, as I said to you, there are lots and lots of interrupts available. We just take one example and we call hardware interrupt. Hardware interrupt mean is connected to the pin, one of the pin of the microcontroller, which is the PB node. Software interrupt is inside a register, keeps incrementing. When it reaches the maximum value, then it causes the interrupt. This is a hardware interrupt example. Okay. So we need to write an assembly language program that counts the number of people passing through a door. So there's a door, like in a library, you go, and every time you cross, it just counts the number of people. And you can assume that only one person can go through the door at any given time. When the total number of people pass through the door reaches a value of 9, so it can only allow 9 people, that's particular room. The warning light LED is lit and the door is locked. So this is the door. This is the door as a switch. You have set it. And this is the warning LED. And there are a couple of other LEDs here. Or you can have a hexadecimal display here as well. You can have that as well if you want it. So the number of people going through the door must be displayed using a 4 set of LEDs or using a 7-segment display which you already have set up for previous experiments. And there should be a reset button. We need to press the reset button. As soon as you press this reset button, then the counter is reset and it starts to count again. So it's count person number 1 went through the door, person number 2 went through the door, person number 9, and that's the maximum you can go through the door. Then the red light glows and everything is disabled. And the operator comes, so that the person at the gate comes and see, everybody has gone now, reset, then they allows the next batch of 9 people to come in. A simple example. And you see, in order to create a hardware interrupt, I've connected that to our RB node, that's that pin, the switch. So this is the one going to cause the interrupt now. So it's a hardware interrupt. Hardware interrupt can only happen at port B RB node, this bit. Note that you are not required to include a switch debounce. Assume that there's already a switch debounce circuit built in. Within the switch you can have as a built-in switch debounce. In some cases you have. So how do we write the program for this? And where is the interrupt service routine going to come into play? So you can see that every time your main program is running, that's the main program, is keep looping. That's your main program. And every time there's an interrupt, say interrupt occurred there, and your program then leaves the main program, go and service your interrupt service routine, and then return it to the main program there. So that's how you write the program. So let's have a look, how do we do this? If you look at the next, the program I've written, it's a single interrupt. Let's see how I've done. I have temporarily stored a location here, H20, status temp is H21, counter in H22. And these are for main program, and these are for interrupt routine. We know already, the computer knows already, it always jump to, when an interrupt happens, go to that address, that's where you should store the interrupt vector. It picks up the address there and then go and execute it, okay? So first part is initialization, that's the initialization. So in the initialization, we select the bank cell, memory containing the AND cell, and then clear AND cell mean port C is digital, clear F AND cell H mean port B is digital, that's we already know. Then we select the bank cell TRISC because we want to make sure that one of the pin is input, all the others are output. So here it's going to be input. So what we want to do is that in this one, we want to make sure that this pin is input for C, and all the others are, that ones are all output. So you set this value, and you send it to that particular address. Now you're going to make this is input because that's your interrupt going to happen. So you have move value binary pattern and send that to B register. Now you select the port C now. So you go to answer, bank select port C, and then clear everything to be 0. So it clears everything to be 0. And clear the counter, whichever counter you're going to use, because you're going to count. So counter is H22. Now, you may ask a question, why do we have those two things? Okay, have a look at this a bit carefully. When the interrupt occurs, at that point, I finish the current instruction. When I finish the current instruction, there are 2 registers I need to make sure I store them. Because those 2 register values belongs to this main program. So one register is the status register, one is a status register, and the second one is the W register. Because the value stored there at the end of that instruction belongs to this program, not for the interrupt service routine. So what I need to do, I need to make sure before I jump here, I need to make sure, when I jump, as soon as I jump from interrupt vector from here to here, the first thing I need to do is, before I execute this program, I need to store these registers which belongs to there in a temporary location. That's what I'm doing. I'll show you in the service routine. So I need to have always two locations initially set up as a memory location where I'll be storing temporarily the status register and W register. Okay, we have initialized the program now. Now we go to the next page, to the main program. So this is like part of the main, but initialization part. So now in the main program, what do you need to do? Now I need to prepare for my interrupt. So enable the external interrupt, because the interrupt is occurring on this one, which is that edge. We're going to detect that edge. So I said bank select option register. We know option register what we need to look at, and we need to look at the 6th bit of the option register. So we go at the 6th bit, that's that one. By setting that bit to 1, by clearing that bit to 1, it detects the falling edge. That's the falling edge. So I want to BCM in clearing that bit. I've set this bit equal to 0. So I've made this pin sensitive to falling edge. Then I select bank cell IN_INT_CON. So first one is option register, and then other one is interrupt control register. And I'm enabling the bit, because I've now set port B ready for receiving it, but I need to tell the computer I want to enable you so that you can receive. So I enable the RB node by setting INT equal to 1. So INTE, if you look at it, is bit 4. So I've set bit 4 to 1, S means setting. Then I want to clear the flag bit, INTF. Because initially I want to make sure that if I clear it, then whenever this becomes 1, I know an interrupt has occurred. So I clear them, BCF, at the first bit. That's bit 1 is cleared. I also have to enable the GIE. GIE said all interrupt should be initially, before you start to do this particular interrupt, to be enabled. So enabling is done by that, because that's a good command, because it can disable all the interrupt. So by enabling it, you have enabled the interrupt. But then by doing this one, you have actually enabled that particular interrupt, not all the interrupt. This is global enabling, and then this is the particular one enabling. So I set that as well. So I have now set I've now enabled the interrupts. Now we need to wait in a loop, and what do we need to do? Okay. I move the counter content to the W register. So counter is initially 0, move that. And I exclusive OR with the hexadecimal 9, because maximum 9 I can have. And then I check for the Z bit. Skip next instruction if it is 1. If it is not 1, that means we still can allow people to go in. In that case, I will just go to wait loop and repeat this again. As soon as I have 9%, this register will be 0, exclusive OR will cause 0, and then I jump out of it and go here. First thing I do is turn off all lights first. I turn off all the lights in case if they were there. Then I turn on only the warning light, because 9 people have gone through. That's warning light is 4, pin 4. So I turn on that light. And then I say that I have turned over the light. Now I want to clear disable the interrupt. So INTF should be disabled. That's equal to 0. Sorry, not that one. Beg your pardon. That's equal to 0. So I've disabled the interrupt. I'm not enabling. Disabled the interrupt. Because 9 people have gone through, I don't want any more interrupt to happen. Okay. Then I go to rest of the loop. This one is port C7. Test bit 7 to see if a key is pressed. That is this one. If anybody has pressed the reset key, I need to check that. Is the reset key pressed? Then I got to set the counter again. So if you test it and if it is not pressed, you go jump from here. If it is pressed, you jump. Otherwise, you go back and keep testing it, right? And when you jump, you clear the counter because you have finished 9 people. You're going to freshly start, and then port C again, 4th pin, and set that pin to enable external interrupt and go to wait loop. So this is what will be happening. But the question is, where is my interrupt service routine? I've written it separately. What happened is, it has to be written separately because while you are in the program here, once you have enabled it, any time interrupt can happen. If interrupt happens, it goes out of this particular loop to the interrupt service routine. So let's look at the interrupt service routine. How does it work? So this is your main problem. Here is the interrupt service routine. Remember interrupt service routine? Current instruction is doing it, and as soon as interrupt happens, this automatically happens. We don't need to do that. It saves the return address first. And then it automatically jumps to this interrupt vector where we have to store the address where the interrupt service routine is stored. But assembler does it for you. So you don't need to worry too much. You come to the interrupt service routine. Remember, in the interrupt service routine, first thing you have to do is you store your status register, W register. So this is the instruction. Remember, we had these two set up earlier. So this instructions save the content of the W register as well as the status register. And then now what do we do? Come to the main function of the interrupt. Because every time a person goes through, interrupt cost, so we increment the counter. Once we increment the counter, you move that into the W register. And you will have to make sure that we are only interested in the 4 bits because we only have to display the counter value. So we do an AND function to the W register. So we only keep these 4 bits, and these are gone. These are all 0, 0, 0. These 4 bits are now sent to the LED lights or hexadecimal display. That's what you are doing. That will display the number, how many people have gone through, right? And then once you have finished that, that's all your interrupt service routine is, So this is initially. Now you need to put all your stored value back into the register before you return. Your return is here. Before you return, remember, you have got to make sure that you are ready to accept next interrupt. So you have to clear the interrupt flag bit. Because as soon as the interrupt occurs, interrupt flag bit is set. And as soon as it's set automatically, you need to clear before you leave the routine. Because when the next interrupt comes, if you don't clear it, this will be equal to 1 and further interrupt won't happen. So you must clear. Now the question is, this is all fine, this is all fine. Here, you restore the register. First one you did it status register. You put them back from the memory to the W register, from W to the status register. You put them back. Now one of the problem always happen is here. The next 2 instructions that you do could affect the status register. That means if the status register is altered, then when you return, it will have a different value than the original saved value. It can happen. So in that case, what do we do? So in that case, so what we need to do is you need to use swapf or move instructions to make sure they do not affect the status register. It's important that, because we need to retain the original status content at the main program. They are saved here, and you are trying to restore, and are there any instruction you do here may affect the status register, then you can't. So what we normally tend to do is this: we use the swap register. Swapping is mean your upper and lower nibbles are exchanged by doing this one in the memory itself. Then you do again in the W register. So your values stay there. They don't affect the status bit at all. So you do this instruction, or you can do move instruction as well. You can check that. This doesn't affect the status register. This doesn't affect the status register. So when you return, you will have the right value. So it's important that you make sure that during this operation, your status register will change, but you need to recover them. What you stored there, you need to recover them, and then you return here, take the address, goes back, and execute the next instruction. So in the interrupt service routine, once you have set up the interrupt, it's very, very easy that you have a main program, you have an interrupt service routine separately, and keep the interrupt service routine, to the minimum. You don't need to write a lot. You can write them all in the main program. Interrupt service routine just does the required service function. So here's the laboratory activity. Activity 7 is a lift control system I want you to do, and you have a PIC microcontroller, and if somebody is used in a lift where somebody pressed the alarm switch. As soon as you press the alarm switch, and you need to program this for the interrupt, and it will flash the LED at 2 Hertz, and it will be flashing until the operator comes and reset. So that's the exercise. And then there's a small question there at the end for you to answer why we have to use interrupt. Can't we poll? Can't we keep reading that particular switch? What's the advantage? So you need to, at the end, you need to just think and decide, have a group discussion among yourself and see what answer you come up with this one. And then you ask the tutor. So again, now that's the last part of it, and again I have used these references which you can also use them, and this chapter is about interrupt.